excuse me, suppose T from V to V be a linear operator, then, and suppose T of V is lambda V for some V not equal to 0, that is, suppose V is an eigenvector of T. Can you define what is its algebraic multiplicity? Of lambda, this eigenvalue? Oh. Yeah, Amog, please. Could you just recall what is the algebraic? I mean, it was actually a simple thing. Do you recall what is the characteristic polynomial of T? You recall, right? And so, algebraic multiplicity of lambda. Yes, the number of multiplicity of lambda. That's right. Yes, the multiplicity of lambda as a root of the characteristic polynomial of T. Okay. Amu, could you please just come forward in this room? So now, geometric multiplicity. So, your name is behind Shandip? You? Oh, what's your name? No. By the side of Snehmai? Yeah. Anvesha. Okay, Anvesha, do you recall what is geometric multiplicity? Number of, you are going quite in the right direction again. Well, not unique eigenvalues, but the number of eigenvalues which are linearly independent and with the same number of eigenvectors which are linearly independent corresponding to the same eigenvalue. Okay. So we define at first eigenspace of lambda as the kernel of T minus lambda I. Okay. I is the identity operator. Okay. That is, T minus lambda I just means that if you apply T minus lambda I on this eigenvector V, Anvesha, are you paying attention? So T minus lambda I of V is 0, right? Because TV is equal to lambda I. Okay. So eigenspace of lambda is just kernel of this, and then, well, you can use a shorthand notation E lambda for eigenspace of lambda. Okay. And then this geometric multiplicity is nothing but the dimension of E lambda. Okay. The number of linearly independent vectors, I mean the maximal set of linearly independent vectors, the coordinate of that in that space E lambda. Okay. So what are we going to prove today? This theorem. Algebraic multiplicity is larger than or equal to geometric multiplicity of any eigenvalue. Okay. And how should we proceed? Well, we'll take, for example, take this lambda and assume, yeah, Manidip? Yes. 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 Right. Right. Yes. Not unique eigenvectors. Eigenvectors are never unique. That is, if you have an eigenvector, any multiple of that is going to be again an eigenvector. Okay. Yes. No. Yes. Any non-zero multiple. Sorry. Yeah. Please go on. Yeah. Yes. Yeah. Right. How many as I mentioned, eigenvectors are never unique. In fact, how many eigenvectors? So suppose you are considering a real vector space, and suppose you have some some linear operator T. I mean, take your favorite vector space, as you said, R2, say, okay, T from R2 to R2. Lambda is an eigenvalue of a linear operator T, okay, all right. So now you are asking how many eigenvector can T have corresponding to lambda, right? Yes, because take any multiple of this, which is a non-zero multiple of V, that would be an eigenvector of T, right? Okay. So was that the question? Okay, Monibi, thank you. Okay, so all of you understood his question. That is, he asked, corresponding to one eigenvalue, how many eigenvectors could be there? And actually, that means, I mean, if V is an eigenvector of lambda, note that anything in its span also satisfies this equation. Well, we disregard 0, because of course 0 would satisfy that as well. But disregarding 0, you will have, at least if it is a real vector space, you will have infinitely many such things. Or, but if you have a finite field, which we haven't formally introduced what is a finite field. At the first class, we told something about modular arithmetic, but then we proceeded further with real vector spaces. But there are fields which are finite many elements are there. But still, it will, I mean, this equation would imply that in that finite field, I mean, take the multiples from the finite that field, all the multiples of V would again be an eigenvector of T, okay, corresponding to the same eigenvalue, lambda, okay. So this is, I mean, finite field will not give you at least infinitely many eigenvectors from here, but you will get as many multiples as multiples of V as there are elements in the field F, of course minus 0. I mean, so it is, if there are n elements, you will get n minus 1 non-zero multiples of V. Okay. Yes. Yes. T. T means. Yes. So T will have a matrix representation. I mean, once you have a basis, you will have a matrix representation of T or T minus lambda. T minus lambda is also now an operator. I is the identity operator. So this will also going to have a matrix representation. With this, I mean, given any basis, you will have a matrix representation. This entire. Okay. Yes, Manas. Yes, of course, you can. Okay. So earlier I mean, in the previous class, we considered this matrix. Recall the identity matrix. How many eigenvectors are there of this? I mean, not how many eigenvectors. What are its eigenvectors? Any element in R2, okay? And so, any element in R2 means that you can choose any pair of linearly independent eigenvectors, right? Okay. Yes, Saidam. Exactly, yeah, right. So now let's prove this, and how should we prove? We'll start from here, okay? That is, we'll start from the geometric multiplicity. So let's assume R as the, I mean, let's take R as the geometric multiplicity of lambda, okay, of some eigenvalue lambda of T, okay. And then, well, let's clear up this part, because this, I think, everybody got what is algebraic multiplicity and what is geometric multiplicity. Amog, is it fine also? Okay. If you have any questions, you can also ask me instead of your neighbor. I can hear the humming sometimes. And if I figured you humming, I am going to ask the question then. So it's your chance to get me before I get you, okay? So R, suppose it is a geometric multiplicity of lambda, and B lambda, suppose it's a basis of E lambda, the eigenspace of lambda, okay? What are we going to do? Recall T was a linear operator from V to V, right? So now we have a basis of one of its subspaces. We're going to extend it to the full basis. Okay. So B, which is B lambda and some extension, so B dash, is a basis of V. Okay. So this is the extended basis from B lambda. Extension of B lambda to a basis of V. Okay. Now what are we going to do? We are going to write the matrix of T in terms of this basis. Okay. So then, okay, let's write it here. Let A be the matrix of representation of T with respect to the basis B of V. Okay. That means T of B is equal to BA, right? So we are, I mean, T of B is just T of this and T of this, T of all the elements here and T of all the elements here. So you can write this as T of B lambda, comma, T of B dash, and here you have B lambda, B dash, and this matrix A, right? But what is T lambda? T of B lambda. This was an eigenbasis, not eigenbasis, a basis of the eigenspace E lambda. Okay. So that means when you do T of B lambda, you are just getting lambda times all the vectors in this. Okay. So you can write this as lambda times B lambda, meaning you are multiplying with lambda all the vectors in B lambda. Okay. And this is some T of B dash, you keep it as it is, and here you have B lambda, here you have B dash, and now you could see what form this matrix would have. Note that this is lambda B lambda and this is B lambda. Okay, so every vector here is just, I mean, this one, the things in this part is just a multiple of the things in here. Okay, so you will have here lambda, lambda dot dot dot, lambda, and R cross R matrix, right? I need a little bigger space. I will wipe this out and rewrite it again. I'm rewriting this, the same line. Wait a minute. Just I need to shift a bit left. Lambda B lambda TB dash, sorry. This is equal to B lambda B dash and this matrix lambda dot 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 lambda, all lambdas on the diagonal, some R cross R matrix, and then what will be this part here? 0, right? Because you are just writing this one as linear combinations of B lambdas, and these are just multiples of B lambdas. Everything else is 0, right? So it's a big 0 here. Okay, and here are some other things. Here are some other things. Okay, all right. So this is the form of A, and since every vector is uniquely represented as a linear combination of basis vectors, this will give you the fact that this itself is equal to the matrix A. Okay. Now we claim that the characteristic polynomial of A, that is the characteristic polynomial of T, because the characteristic polynomial of T is defined to be the characteristic polynomial of the representing matrix with respect to any basis. Okay. Yes. Which part? CD, some linear combinations. I mean, these are some matrices. Here we have a specific form. This was lambda b lambda, and the first part is just lambda times that corresponding vector. And here you do not know what they are. So we are just putting some random I mean, the C and D would be of the right size. This is R cross R, and this is some n cross n if n is a dimension of V. So you just fill in some arbitrary entries here. You can fill it with stars as well. You do not know what entries are here. So we just put C and D there. Which one? This part? Okay. How do you write these ones, lambda b lambda, in terms of, I mean, suppose your b lambda is equal to v1 dot 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 vn. Then what is lambda b lambda? Is lambda v1 dot 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 lambda vn. All right, Shotrik? So you are trying to write lambda v1. Now, what this first column gives? It is the linear combination of v1 to vn that would give you lambda v1. Okay. Now, what linear combination of v1 to vn is giving you lambda v1? It is lambda times v1 plus 0 times everything else. Okay. That's what I wrote here. It's lambda times v1, and so this column is giving you the linear combination, right? The second one would be lambda times v2 and 0 times everything else. That's this. Okay. And dot 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 up to, well, here there was a first R things only, excuse me. So this is R and this is R. So this lambda VR is again lambda times VR and 0 times everything else. So this is the first matrix. This part is 0. I mean, this has no contribution from B dash, right? Because B dash, I mean, this will extend to VR plus 1 or Vn n, and all these coefficients of these ones would also be 0. So this is just a 0 matrix. Okay, all right. And here you do not know what entries are there, so you just put some C and D there. Okay. But thank you, Shutri, for the question. I hope this form is clear to everyone else. If not, please ask me again. We can explain it again. So you are getting it? Excuse me. Your name is? You at the end. Yeah, it's fine to you as well. Could you please just come to the front? And Liam, you also please. Avinav, right? Avinav, please also there. Your name is? Yeah? Straddle. Struggle? How do you write it? Pronounce it. S-H-R-A-G-A-L. Struggle. Okay. Thank you. Yeah. Okay. So, struggle, this form of matrix is fine. Avinav? It's all right? Okay. Okay. Now, what we are going to do, we are going to write a claim that is the characteristic polynomial of this will have this form t minus lambda whole power r, and the characteristic polynomial of sorry, not this, p d. Note that if we prove this claim, then we are done. Why? Because we just see from here that t minus lambda whole power r then divides this one, right? P A t. What does it mean? The multiplicity of lambda as a root of this is either r or larger than that, right? So that means algebraic multiplicity of lambda is larger than or equal to r, right? So we just need to prove this. All right. Yes. T v dash in terms of linear combination of? Not necessarily. T v dash is just you are applying t on b dash. It could have contribution from here and as well as there. Okay. Yes. Yeah. What is small? T is a variable. Okay. So how do you define the characteristic polynomial of T? Let's recall. Mohit, could you please define this characteristic polynomial of a matrix A? Almost. Okay. It is, we define it by Ti minus A because it's a polynomial. Okay. By lambda we will prefer to denote the eigenvalues. Okay. And then we just write Ti minus A. Why we take T? Of course, you can change the convention. You can write A minus Ti, but we stick to this convention just to make it a monic polynomial. The first coefficient is then T power n. Okay. Yes. Yeah. Why? Oh, we claim that because of this. I mean, once you have this, if we could prove this claim, suppose, then that would mean T minus lambda r is dividing this characteristic polynomial of A. Isn't it? Because you are writing that this is this times another polynomial. Okay. So that just means that I mean this one is dividing this one, right? And that means that the multiplicity of this root lambda in this is r or higher. Okay. I mean there could be some T minus lambda also come from here. Okay. So that's why we get that algebraic multiplicity of lambda, that is the multiplicity of lambda as a root from here, is larger than or equal to this r. Okay. So Deepto, is it clear to you as well what T is? It's just a variable, right? You could use x instead, okay, or z or y. Okay. All right. Your name is again? You? Yeah. Shankar. Okay. So yes. So is it fine for you too? What is the characteristic polynomial and what is T? Shankar, I'm asking you. T is just a variable. Okay. Yeah. Yes. PD. What? PD. It's just a characteristic polynomial of the matrix D. Okay. This is D. This is some matrix D. Okay. All right. So let's prove this. The proof is rather straightforward. Yes. Yes. Have you seen that in linear algebra 1? I mean, not linear algebra 1. This is this course. In the earlier course, you haven't, right? So let's prove it then. Okay. How do we prove this? All right. At first, well, we begin with induction. Okay. So what do we do? Suppose r is equal to 1, the first case. Okay. And then A is of this form, lambda and all zeros here. Okay. And this is just a row. We should have ideally written r here instead of C because it's not a column but a row, but that's our convention. So I mean we started with this. So let's still write here C for this row and D for the rest of the matrix. Okay. And then we get that the characteristic polynomial of A would be then Ti minus A, right? So the first thing would be T minus lambda, and then you have the characteristic polynomial of this one. So it's trivially true, right? That would imply PAT is indeed equal to T minus lambda times PDT. Okay. So this is true as again. Okay. Right. Thanks a lot, Dipto, for pointing out the thing that this D could have a higher dimension. Now suppose the claim also holds for r equal to m. So what we are going to do now, we would like to prove this for r equal to m plus 1 then. Yes? What? How do you expand a determinant? Right, you can expand it with a column, right? So if you expand it with this is t minus lambda and ti minus d, determinant of that, right? Okay, and then all this is 0. So these are, I mean, from C you are not getting any contribution at all. So just by the definition of determinant, I mean, how do you expand it with the first column, you are getting it. Okay. So is this point clear to everybody? Manas, is this fine? Sairam? This, I mean, why? Yes. Right. That's the logic. Perfect. Yes. Indeed. Yeah. That's what we do. So here we are going to write down just what Sairam mentioned now. Okay. That is the case r equal to m plus 1. Okay. Then what form does A have? A is, well, it is having now m plus 1 things. So take the first one out. Okay. Here are zeros. Here are some entries that you don't know. And here there are lambdas. How many? Now 1 less than m plus 1. So that is m cross m. And here there is some c dash. Here is the d. And here everything is 0. Okay. So this is the form of A now we are considering. And what we are going to do? Well, for this one we have induction hypothesis. And so we just expand again with the first column. Okay. And then we are just having another factor t minus lambda coming from there. Okay. And this one we are done by the induction hypothesis. Okay. So PAT then is t minus lambda times t minus lambda whole power m and the characteristic polynomial of d. Okay. So that is just t minus lambda whole power m plus 1 pd t. We are done. Okay. So that finishes the proof of this claim, and hence the proof of this inequality. Okay. I hope the argument is clear to everybody. All right, Mohit. Now a short exercise for you. Can you figure out the characteristic polynomial of this matrix? Just compute the characteristic polynomial of this matrix. Okay. Okay. Wait a minute. I'll write it down here. Okay. So characteristic polynomial of A, B, C, D. This is, yeah, tell me. No, the opposite, T minus A. Expand it. Expand it and write it down. I mean, write it as a polynomial in T. Okay. T squared, right? T squared minus A plus D times T plus AD, just AD. Is it minus BC forward, right? It is AD minus BC. So what is this A plus D? It is just the sum of the diagonal terms, right? The trace of this matrix. And what is this? This is the determinant of the matrix, right? So, for a 2 cross 2 matrix, you have this is T squared minus the trace of A times T plus the determinant of A, right. Something similar also happens when A is an n cross n matrix. So, suppose A is now n cross n, and the claim is that now AT is equal to T power n minus trace of A times T power n minus 1 plus some intermediate terms plus determinant of not plus, excuse me, plus minus 1 whole power n determinant of A. Okay. So, have you seen this earlier in the previous semester? No. Okay. All right. So, I can give you a hint how to do this. What is PAT? The characteristic polynomial of A, right? Write it down here. Determinant of Ti minus A is this one, right? Oh no, we have not proved it yet. So, it is not defined in this manner, but we are trying to prove that this is equal to this. Okay. So, how do you get the constant term? Given a polynomial, how do you get the constant term of that? Put T equal to 0, wonderful. So, you put T equal to 0 here, you get determinant of minus A, right, and A is an n cross n matrix. So, that minus sign would go out with this at whole power n, because determinant is, well, because determinant is linear in the row, it is a multilinear thing. Every row is multiplied with minus 1. So, you get a minus 1 out for every row, okay. That is minus 1 whole power n, minus 1 whole power n times determinant of A. Well, how about this trace of A? Okay. I will give you this as a easy homework to you. So, try it at home. It is nothing but writing this one again explicitly and expanding and taking a note of the powers of T. It is not difficult. Okay. So, HW is to prove that this is indeed true. Okay. Once you have this, and once you have this proposition, one could draw this corollary from here, that given a matrix A for any square matrix A, eigenvalues lambda 1 dot lambda n, not all necessarily distinct. So, some of them could be the same. You have trace of A as the sum of the eigenvalues lambda 1 plus dot dot plus lambda n, and the determinant of A as the product of the eigenvalues lambda 1 dot 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 lambda n. Why? Yes? The Weierstrass formula, what is that? Weierstrass formula? Exactly, yeah. So, if you write down the, so lambda 1 to lambda n is, lambda 1 to lambda n are just the roots of the characteristic polynomial, right. So, you may write PAT as PAT is T minus lambda 1 times T minus lambda 2 dot 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 T minus lambda n, right. And then the first coefficient here is T minus lambda 1 plus dot 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 plus lambda n times T power n minus 1 plus dot dot dot, the nth coefficient is minus 1 whole power n lambda 1 dot 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 lambda n. Okay. So, So just compare this and this, and you are done. Okay, now a small detour about sums of subspaces. Okay. So suppose W1 dot 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 Wk be subspaces of a vector space V. Okay. We define their sum as the expressions of this form W1 dot 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 Wk, small W1 dot dot Wk, such that small Wi is in capital Wi. That's a straightforward definition, and it is easy to check that given a set of subspaces, their sum is again a subspace of V. Okay. And now we are going to define independence of subspaces. Okay. Okay. So W1 dot 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 Wk are said to be independent if for if given small W1 dot 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 small Wk equal to 0, where Wi is an element of Wi, we must have each of these things W1 to Wk be equal to 0 for all I. Okay. All right. So that means what that means, before we say it in words, let's just imagine. Okay. So suppose this x-axis is your W1 in R2. Okay. Now the first question is that is the set of subspaces which are independent of W1, how many elements are there? Is there a unique element, or are there more elements which are independent of W1? Yeah, you. So give me an example first of a space which is independent of W1. Very good. Each line which is not the same as W1. Okay. So any line is a linear subspace, right? And in its intersection that intersection with W1 is just having 0. In other words, linear independence, what you learned earlier for vectors, is just the independence of linear subspaces. Okay? Linear independence of spans of vectors. Okay? I mean spans of singleton vectors. Okay? And in probability, perhaps you have seen that mutual independence doesn't imply global independence, right? That's true. I mean that's as well true here. So for example, suppose this is W1, this is W2, and this is W3. You see that W1 and W2 are independent. W2 and W3 are independent. W3 and W1 are independent. But are W1, W2, and W3 independent? No, because take any vector here. Okay, that's a linear combination of this and this. I mean something here and something there, right? Okay. All right, Shotrik, are you following? That is, mutual independence doesn't imply global independence. That is, W1, W2 independent, W2, W3, W1 independent doesn't imply that W1, W2, and W3 are independent. Okay, because there is a non-trivial solution to this here, right? you can take this one as say 1 1, this one as minus 1 0, and this one as minus 0 1. That's equal to 0, right? This is in W3, this is in W1, W2, and this is in W1. Okay, so that's what I just meant. Okay, now if okay, before writing that, I mean what I was going to write, I would like to give you another small homework. It's rather trivial because you have done spans of vector spaces rather well and rather slowly as well. Okay. So what I'm going to write is this. This theorem, no, it's not. We cannot call it a theorem. It's rather simple, as I mentioned. Let's call it a homework. Okay. So let W1 to Wk be subspaces of V, and let B1 dot Bk be their respective, I mean be a set of respective bases, be basis of W1 dot Wk respectively. Okay. Then the following are equivalent. There is a shorthand for that. I hope you also use this. That's easier for taking notes. The following are equivalent. Okay, what are those? Yeah. So the first one is W1 dot Wk are independent, and W1 plus dot plus Wk is equal to V. Okay. And the second one is that B defined as a composition of B1, I mean just an augmentation of B1 B2 dot Bk. This is a basis of V. Okay. And it's not much difficult to see through the equivalence if you recall what independent means. That is, the only relation among W1 to Wk is trivial when all the components are 0. Okay. And that would imply that all the linear combination, I mean the linear combination of B1 is the elements in B1 is 0. The linear combination of elements in B2 is 0. The linear combination of elements in Bk is 0. Provided, I mean, if you have a linear combination of these to be equal to 0, all the components would be individually 0. Okay. And that will give you that this is a basis. Okay. And on the other hand, if this is a basis, of course you can see that the span of this, the span of this all are independent, okay, because this entire set is linearly independent. Okay. And that they span V, of course it's a basis. A linear all the linear combinations are giving you all the vectors in V. So this, as I mentioned, this is a rather simple exercise. Okay. Now, no, this one is the last board. Yeah, this one was previous board. That one was the last board on the left. Okay. So now we draw two corollaries from this. Before we draw any corollary, we introduce a notion of direct sums. Okay. If your spaces W1 to Wk satisfy any of these two conditions, 1 or 2, direct sums, if W1 dot Wk satisfy any of the conditions in the previous theorem or previous homework, satisfy the conditions or equivalently 2 of the HW problem, we call W1 dot 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 WK. No, we don't call them anything. We already say that they are independent. We write V is a direct sum, which we denote by this, of these subspaces. Okay, direct sum of W1 to WK. All right. Okay. Now a quick example. Suppose T is a linear operator, lambda 1 to lambda k be its eigenspaces corresponding to distinct eigenvectors now, lambda 1 to lambda k. Okay. So here's the theorem. Let T from V to V be a linear operator with okay, operator stop there, and then let lambda 1 to lambda k be distinct eigenvalues of T. Okay, we are not saying that they are all the eigenvalues, all the distinct eigenvalues. Suppose this is a set of distinct eigenvalues. Okay, a set of distinct eigenvalues of T. Okay, then E lambda 1 dot 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 E lambda k are independent. Okay, the proof is rather simple. So let E lambda I be elements in E lambda I such that you have a relation like E lambda 1 plus dot 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 plus E lambda k, which is equal to 0, where not all E lambdas E lambda I are 0. So if all are 0, then there is no contradiction to the independence. So we are proceeding by contradiction. Okay. So we are assuming that there exists such a relation such that this, I mean, there is a non-trivial relation among the elements E lambda i's. Okay. What we do now, we just apply T on this. Okay. What we get by applying T on this? We get T E lambda 1 plus T E lambda 2 plus dot 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 plus T E lambda k to be equal to 0, right? And that gives you lambda 1 E lambda 1, because it was an eigenvalue, eigenvector in E lambda 1, you get lambda 1 E lambda 1, lambda 2 E lambda 2 plus dot 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 plus lambda k E lambda k equal to 0, right? So we are getting two linear relation, I mean two relations among this. One is this one, call it the first equation, call this the second equation, okay? And then, all right, wait a minute here, okay? Note first that this claim is true if k is equal to 1, right? Because it's an eigenspace, okay? And an eigenspace consists of vectors which are non-zero, right? So there exists at least one non-zero vector there. So if you have just E lambda 1 equal to 0, it has to be 0, okay? So the claim is trivially true. The claim is trivially true for k equal to 1. Okay. And now we can assume k to be larger. Okay. And we can proceed by induction hypothesis. So suppose this is true for k minus 1. Let's assume. Okay. Let's assume the claim holds for k minus 1. We are going to show that it holds for k as well. Okay. So this is the relation. What we do now, we multiply this first equation 1 times lambda k, and we subtract the second equation from this, and that would give us lambda k minus lambda 1 E1 plus dot 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 plus lambda k minus 1 E lambda k minus 1 equal to 0, right. Note that this is just a multiple of lambda 1, and E lambda 1 was an element of this space E lambda 1. So this entire thing is inside E lambda 1. This entire thing is inside E lambda k, right. So you are having a relation in the set E lambda 1 to E lambda k such that their sum is equal to 0. And this, we said that this, by induction hypothesis, that is, we assume that the claim is true for k minus 1, right. So that would give us that each of the individual components are equal to 0, right. So that would give you lambda k minus lambda I times E lambda I is equal to 0. Okay. And that would mean that E lambda I is equal to 0. So this is for all I less than equal to k minus 1, and then this again for this I less than equal to k minus 1. Why? How from here to here we can come? Yes, these are distinct eigenvalues, right. So lambda k minus lambda I is, oh yeah, just 1 minute. So lambda k minus lambda I is not equal to 0, and therefore that will imply that E lambda I is equal to 0 for all these i's. Okay. So that would mean that the entire first part up to E lambda k is equal to 0. That would mean that E lambda k is itself also 0, because the sum is equal to 0, right. Okay. So we are done with this. Okay. So that finishes the proof. That would imply that E lambda k is also 0. Okay. So we are going to use this proposition in the next class. Okay. That's all for today. Thank you.